December 7, 1941, 7:55 a.m. Pearl Harbor burns under a sky filled with Japanese aircraft, and 22-year-old Staff Sergeant James "Jimmy" Patterson watches his entire squadron of P-40 Warhawks reduced to twisted metal and flames in less than 10 minutes. But here's what nobody expected. In just 6 hours, this young mechanic from rural Kansas would perform what military historians now call the most impossible aircraft repair in aviation history, using nothing but a Coca-Cola bottle, fishing line, and the kind of stubborn determination that only comes from growing up fixing farm equipment with whatever you can find in your father's barn. But first, you need to understand just how hopeless the situation really was. The irony wasn't lost on him as he watched months of careful mechanical work disappear in seconds under waves of Mitsubishi A6M0s and Nakajima B-5N torpedo bombers. Patterson counted 17 P-40s completely destroyed, 3 more damaged beyond any reasonable hope of repair, and exactly 1 aircraft that might be salvageable if a miracle happened to walk through the hangar doors. That miracle was about to come in the form of a farm boy who had learned to make the impossible work with whatever materials happened to be lying around. The surviving P-40E Warhawk sat in Hangar 7, its nose cone cracked open like an egg, hydraulic lines severed, control cables snapped, and a hole in the fuel tank large enough to put your fist through. Any rational person would have written it off as scrap metal. But Patterson wasn't looking at scrap metal. He was looking at the only hope his unit had of getting even 1 fighter aircraft back in the sky before the Japanese returned for what everyone knew would be a second wave of attacks. Lieutenant Colonel David Matthews, the base engineering officer, surveyed the damage with the grim expression of a man watching his career end in real time. "Patterson," he said, his voice carrying the weight of defeat, "I need an honest assessment. Can any of these birds fly again today?" The question hung in the air like smoke from the burning oil tanks outside. Patterson walked around the damaged P-40, running his hands along the twisted metal, listening to the sounds the aircraft made when he pushed against different sections. This wasn't the methodical inspection they taught in flight school. This was the intuitive understanding of mechanical systems that comes from a childhood spent coaxing life out of broken tractors and farm equipment that should have been scrapped years ago. "Sir," he said finally, "give me 6 hours and whatever materials I can scrounge from the base, and I'll get this one airworthy. We don't have the parts, we don't have the time, and frankly, we don't have the industrial equipment to make those kinds of repairs under field conditions." When the family's 1928 John Deere tractor threw a rod through the engine block in the middle of harvest season, young Jimmy hadn't called a mechanic. He'd fashioned a replacement part from scrap iron, sealed the crack with a mixture of sawdust and engine oil, and kept that tractor running for 3 more years. The P-40 sitting in front of him was just a more complex tractor with wings. "Sir," Patterson said, pulling out a small notebook where he'd already started sketching solutions to problems that didn't officially have solutions, "I need you to trust me for the next 6 hours. If I can't deliver a flyable aircraft by 1400 hours, you can court-martial me for wasting time during a national emergency." The P-40's landing gear, flaps, and gun charging mechanisms all depended on hydraulic pressure, and the Japanese strafing run had severed the main hydraulic lines in 3 different locations. Military protocol called for complete system replacement using factory-manufactured components that would take weeks to ship from the mainland. Patterson had a different idea. He started by draining what was left of the hydraulic fluid into every clean container he could find, including several empty Coca-Cola bottles that the hangar crew had left lying around. The fluid was contaminated with metal shavings and debris, but Patterson had dealt with worse. Growing up, he'd learned to filter tractor hydraulic fluid through layers of cheesecloth and coffee filters, removing contaminants that would normally require industrial filtration equipment. While the fluid filtered, Patterson turned his attention to the severed hydraulic lines. Standard repair procedure called for cutting out the damaged sections and installing new lines with proper military specification fittings. But the base supply depot was a smoking crater, and the nearest replacement parts were 3,000 miles away in California. Patterson studied the damage and realized something that the engineering manuals had never considered. The hydraulic system didn't need to be perfect. It just needed to work long enough to get one more fighter aircraft into the air. The pressure regulation problem led to what would become the most famous improvised repair in military aviation history. The same principle could work with hydraulic fluid, but it would require precise calculations and materials that weren't exactly standard aircraft equipment. The bottle would serve as a makeshift accumulator, storing hydraulic pressure and releasing it gradually to prevent dangerous pressure spikes that could blow out his improvised tubing connections. The string would serve as a measuring device, allowing him to monitor fluid levels and pressure changes by watching how the string moved inside the bottle. He was applying engineering principles that wouldn't be formally recognized until decades later. The Coca-Cola bottle accumulator was essentially a primitive version of the pressure dampening systems that would become standard in aerospace engineering during the 1960s. The fishing line he wound around the bottle cap served as both a pressure gauge and a safety release mechanism, automatically venting excess pressure before it could damage his improvised connections. By 1,000 hours, word had spread throughout the base that the crazy mechanic in Hangar 7 was attempting something that bordered on science fiction. Officers and enlisted men began gathering to watch Patterson work, their expressions ranging from skepticism to outright disbelief. But as the morning progressed, something remarkable began to happen. The jury-rigged hydraulic system actually started working. Patterson tested each connection individually, slowly building pressure and monitoring his improvised gauges with the intensity of a surgeon performing brain surgery. When the landing gear retracted smoothly for the first time since the attack, a cheer went up from the growing crowd of spectators, but Patterson wasn't celebrating yet. He knew that hydraulics were only the beginning of his problems. The P-40's flight controls depended on a complex system of cables and pulleys that translated pilot inputs into control surface movements. Several cables had been severed by shrapnel, and the standard replacement procedure required removing major structural components to install new cables from the factory spools. Patterson didn't have factory cables, and he certainly didn't have time for major structural work. What he did have was piano wire salvage from the base chapel's damaged piano, along with an intimate understanding of tension and load distribution that came from years of rigging farm equipment. Piano wire was actually superior to standard aircraft cable in tensile strength, but it required different connection techniques and careful attention to prevent stress concentrations that could cause catastrophic failures. Patterson spent 2 hours creating custom cable connections using techniques he'd learned from his grandfather, who had been a bridge builder during the early days of railroad expansion across Kansas. Each connection was tested individually under load conditions that exceeded what the aircraft would experience in normal flight. The improvised control system wouldn't win any engineering awards, but it would respond to pilot inputs with a reliability that could mean the difference between life and death in aerial combat. Military procedure called for a complete tank replacement, which was obviously out of the question given their time constraints and material limitations. Patterson studied the damage and realized that he needed to think about the problem differently. Using materials from the base fabric shop, including sailcloth and waterproof adhesives, he constructed what amounted to an internal bladder that would contain the fuel while conforming to the tank's irregular shape. The technique was similar to methods he'd used to repair water tanks on the farm, but adapted for the specific requirements of aviation fuel and the stresses of high-altitude flight. By 1,200 hours, Patterson had created something that looked more like a mad scientist's experiment than a military aircraft. Coca-Cola bottles and improvised gauges dotted the cockpit area, piano wire connections gleamed in the Hawaiian sunshine, and the entire aircraft seemed to be held together by determination and ingenuity rather than proper engineering practices. But when Patterson activated the hydraulic system and ran through the complete range of control inputs, everything worked exactly as it was supposed to. But Matthews was also responsible for flight safety, and sending a pilot up in an aircraft held together with Coca-Cola bottles and fishing line violated every safety protocol in the book. The Coca-Cola bottle accumulator would regulate hydraulic pressure more smoothly than some factory-installed systems. The piano wire control cables would actually respond faster than standard cables because of their superior tensile properties. The internal fuel tank seal would prevent leaks while maintaining the tank's structural integrity under the pressure changes of high-altitude flight. First Lieutenant Robert Dutch Schultz had volunteered for what everyone assumed would be either a heroic gesture or a suicide mission. Schultz was one of the most experienced P-40 pilots on the base, with over 500 hours in type and a reputation for being able to fly anything with wings. But even he looked uncertain as he approached Patterson's mechanical creation. "Sergeant," Schultz said, running his hands along the improvised connections with the careful attention of a pilot whose life would depend on every component working exactly as designed, "I need to know that you have complete confidence in these repairs, because once I'm airborne, there's no mechanic up there to fix things if something goes wrong. Sir, I'd fly this aircraft myself if regulations permitted it. Every connection has been tested beyond normal operating parameters. Every system has redundancy built in where possible, and I've personally inspected every component that matters for flight safety. This aircraft will get you up and bring you back down. What happens in between is up to you, and whatever Japanese aircraft are foolish enough to get in your way." Schultz worked through his pre-flight checklist with extra attention to the improvised systems that now controlled critical flight functions. Hydraulic pressure held steady within normal parameters. Control surfaces responded smoothly to stick inputs. The fuel system showed no signs of leaking, and the improvised pressure gauges all indicated that Patterson's calculations had been exactly correct. At 13:52 hours, the most unlikely fighter aircraft in the Pacific Theater lifted off from Hickam Field and climbed toward an uncertain encounter with destiny. Schultz intercepted a formation of Japanese reconnaissance aircraft approaching from the northeast, engaging them in aerial combat that pushed his improvised aircraft to the absolute limits of its performance envelope. The Coca-Cola bottle accumulator maintained hydraulic pressure through violent maneuvering that would have challenged factory-fresh systems. The piano wire control cables responded instantly to control inputs that meant the difference between shooting down enemy aircraft and becoming a casualty himself. The modified hydraulic system provided more consistent pressure under high-G maneuvering conditions. Even the fuel tank repair proved superior to the original design, eliminating a chronic seepage problem that had plagued P-40s since their introduction. The impossible repair had not only worked, but had performed flawlessly under the most demanding conditions possible. The Coca-Cola bottle accumulator became the basis for improved hydraulic systems that would be standard equipment on late-war aircraft. The piano wire control cable modification was adopted for field repairs throughout the Pacific Theater. Over the following weeks, he would perform dozens of similar, impossible repairs, each one building on lessons learned from the first Coca-Cola bottle miracle. By war's end, Patterson's techniques had been responsible for returning over 300 aircraft to combat status that would otherwise have been written off as total losses. The story of the mechanic who fixed a fighter aircraft with a Coca-Cola bottle and string became legend throughout the Pacific Theater, inspiring countless other improvised repairs that kept American aircraft flying when parts and equipment were impossible to obtain. But the real significance of Patterson's achievement wasn't just mechanical. It represented something fundamental about American character, the refusal to accept defeat when determination and ingenuity could create solutions that didn't exist in any manual. The young sergeant from Kansas had not only solved an impossible problem but had advanced the science of aircraft maintenance in ways that wouldn't be fully understood until decades after the war ended. His methods were officially adopted by the Army Air Forces and later by the newly formed U.S. Air Force, where they remained classified until the 1970s. The techniques he developed during those desperate hours after Pearl Harbor would influence aircraft design and maintenance procedures well into the jet age. Modern aerospace engineers analyze his solutions not just for their historical significance, but for insights that remain relevant to contemporary aircraft maintenance challenges. The principles he applied, using available materials to solve critical problems under extreme time pressure, are now taught in engineering schools as examples of creative problem-solving under constraints. The P-40 Warhawk that Patterson saved with his improvised repairs flew 47 more combat missions before being retired at the end of the war. It was eventually restored and is now displayed at the National Museum of the Pacific War, where a small placard tells visitors about the day when a farm boy from Kansas proved that sometimes the impossible is just another engineering challenge waiting for the right person to solve it. But perhaps the most important legacy of Patterson's achievement isn't technical at all. In those critical hours after Pearl Harbor, when America's Pacific Fleet lay in ruins and the future of the war hung in the balance, one young mechanic refused to accept that broken meant beaten. Armed with nothing but ingenuity, determination, and a deep understanding that every problem has a solution if you're willing to think beyond conventional approaches, he demonstrated that American resourcefulness could overcome any challenge. Sometimes the most sophisticated problems require the simplest solutions, and sometimes the impossible becomes possible when the right person refuses to accept that it can't be done. Staff Sergeant James Patterson proved that miracles aren't supernatural events. They're what happen when knowledge, determination, and creativity combine to solve problems that everybody else has already given up on.